Let's start the differential amplifier by talking about the three basic amplifier types: the common emitter, the common collector, and the common base. Now, if you recall, the word common, when we're talking about these amplifiers, is which terminal we're taking to ground. So in a common emitter, what we do is we tie the emitter to ground through a capacitor. In the common collector, we tie the collector to ground, which is to the DC supply. But when we look at the AC equivalent circuit, we short that. So this is tying the collector to an AC ground point. And in the common base, what we'll do is we'll tie the base to ground through a capacitor. And we do that with a capacitor so that we don't disrupt the DC bias voltage. But we tie the base to ground with a capacitor, and then this becomes an AC ground point. So that's common base. So common emitter, common collector, common base. Which terminal is grounded to an AC ground point? On the common emitter, what we do is we put a signal in here. So the input is applied to the base, and the output, which is out of phase, is taken from the collector, the transistor. So input applied to the base, output taken from the collector. And what you're doing in the common emitter is when we take this point to an AC ground point, what we're doing is we're holding that at a fixed value. We're grounding this point, and then when we wiggle the base voltage up and down, we create a changing base emitter current, which gets amplified by beta and results in a big change in the collector current. That collector current is put through a collector resistor, which results in a large voltage swing on the collector. And it's an out of phase. Put in this, get that out. Now in the common collector transistor, what we're doing is we're applying the input here. So we apply our sine wave input here on the base, and we're going to take our output off of the emitter, and we're going to couple that to a load through a capacitor. Now what you can do with this one is you can think of the base and the emitter as effectively having a diode drop between them. So if I put a positive sine wave in over here, if I wiggle this point up and down, that just wiggles this point up and down with it. So what we end up with is an output off of the emitter, which is in phase with the input. And then finally on the common base, now what we're doing is we're grounding the input to an AC ground point, and we're applying the signal. So we're going to apply an input signal to the emitter. So we're going to feed our input in this way. So on this one here in the common base, what you're essentially doing is you're fixing the base at a fixed ground point. You're putting a stake in the ground and you're saying that is stuck at that point, and you're wiggling the emitter side. So over here, we put this point fixed and we wiggle this side to create a changing base current. While over here, we're fixing that point and we're wiggling the other end up and down in order to create a changing base current. That changing base current will result in a beta times IB larger collector current, which will go through the RC collector resistor, creating a voltage drop, an AC voltage drop across the collector resistor. Now when I put this signal in here, when I pull this down, it pulls this point down with it. So this will be in phase. So these 2 points will be in phase. And when I pull this down, I will get a larger current going through the collector resistor, which means that the voltage on this point will also go down. So if I apply an input to the emitter in a common base circuit, I take my output off of the collector and it is in phase with the input. So here, input and output are out of phase, while over here, input and output are in phase. Let's switch over to multisim and show how we're going to take this one and put them together into a differential amplifier. let's start looking at the differential amplifier by looking at this example of a common emitter amplifier. Now this is not a great common emitter amplifier because I don't have a capacitor down here to short out the emitter resistor. But I'm applying an input onto the base here and I'm taking the output off of the collector. And we can see what happens with the gain and the phase shift by looking at this signal. And here I've got channel A of this scope here on VN, and I've got channel B of this scope on VC. So when I pop this up, I can see that here I'm putting an input signal, which is a 1 kilohertz sine wave, and I'm getting out a sine wave, which is a little bit smaller, but it's 180 degrees out of phase. And we do expect 180 degrees out of phase. And although we don't normally expect a smaller output, if we look at the values that I've picked for RC and RE, you can see that RE is bigger than RC, so we should actually see an attenuation here. The gain should be this resistor divided by this one, so it should be about 0.5, which is what we're getting. This output here is about half the amplitude of the input. So off of the collector, we're seeing what we expect. We see an output with half the peak amplitude and 180 degrees out of phase. Now let's take a look at the emitter. And over here I've got another scope. So here I've got VN versus VE. When I pop this one up, we can see that here is the input signal going to the base of the transistor. And then on the output here, I see basically the same thing. I see the same amplitude and it's in phase. And that makes sense when you think of that there's a base emitter diode on the transistor. So essentially as this goes up, this point here is going to follow it. So as VN goes up and down, VE is going to go up and down. AC wise, it's going to be the same amplitude, but DC wise, it's going to be 0.7 volts less. So here we are, we apply the voltage to the input of the transistor. On the collector, we get an out of phase output, and off of the emitter, we get an in phase output. What would be the output impedance if I was to put a load on here? What would the output impedance be? Well, if I look back and I Thevenize this path back to the source, and a source usually has a pretty low output impedance, like 50 to 600 ohms. So if I take that 600 ohms and I divide it by beta, because I'm looking back through the emitter, beta is 100. So you're looking at an output impedance on the emitter here less than 10 ohms. So it's a pretty low output impedance. Now this can actually be connected to and can drive something as a low impedance source. What I've done here is I've taken the same transistor amplifier and I flipped it around, and instead of putting a signal in on the base, I'm going to put a signal in on the emitter. So this is a common base configuration. You can see that I've grounded the base and I'm applying a signal to the emitter. And what we should see is coming off of the collector, this is going to be our output, we should see our sine wave coming out of this point here. So input here, output here. We've got a scope set up here. Here's VN, here's VC. So let's see what happens. So here's the input signal, which is 10 millivolts peak. And here's the output signal coming off of the collector. So we are seeing an output that is a sine wave, and it's in phase with the original sine wave, with the original input. So I'm applying a signal in here, and I'm getting an output off of the collector, which is in phase with the input. So this is a common base configuration. Now the question is, do we need to drive this with a signal generator, or can I drive this with another transistor amplifier, maybe the one that we used in the first circuit? So now I've taken those first two circuits. Here's my common emitter amplifier, and here's my common base amplifier. And what I'm going to do is I'm going to join them together at the emitters. So the source for this common base amplifier is going to be the generator. It's going to be the emitter of the first amplifier, and ultimately back to the generator here with a low output impedance. So we're putting our signal in here, and we should get an out of phase output on the first transistor. But since this is in phase to here, and since this was in phase with this point, we should see an in phase output on the second transistor. So let's pop open our scopes. So here's VN versus VC. So I'm applying an input signal here, and I'm seeing an output sine wave, which is out of phase. It's 180 degrees out of phase with the original input. Bring up the second one here. So now this is this point versus the input. So it's the same input here on the top of the diagram. But now this is the collector. This is this point here. So I'm seeing an in phase output. But I'll also point out that the amplitude here on VC1, this is the amplitude of VC1, and this is the amplitude of VC2. We're getting the same amplitude on both collectors, but one is in phase and one is out of phase. If I apply the signal in on this transistor, then this collector will be out of phase with this input voltage, but this collector will be in phase with this input voltage. So the differential amplifier, we can apply a signal to one of the transistors and we will get equal but opposite outputs on both transistors. So it's one input with two outputs. You may have noticed that I have two resistors down here on the emitters, RE1 and RE2, that are both the same value. They're 2K. You may ask yourself, could I replace this with just one resistor? And the answer to that is yes, absolutely. You could replace these two guys with a single 1K. So let's go ahead and do that. So here we are now. I've placed a single 1K resistor down on the emitter tail. I've also renamed the collector voltages. Instead of VC1 and VC2, I'm now naming them Vout1 and Vout2. And this is more appropriately named for the differential amplifier, which we think of as a two transistor amplifier where we have one or two inputs and we have one or two outputs. So each collector is a potential output. If I apply V in here to the base of Q1, Vout1 should be out of phase with the input because the common emitter amplifier has a negative gain. However, this also drives the second transistor here, Q2, in a common base configuration. So Vout2 should be in phase with the original input. So if I have one input voltage, I will have one output out of phase with the input, and I will have one output that is in phase with the original input. So let's pop open our scopes here and see if that's true. So here's scope number 2, and that's VN versus Vout2, so that's this voltage. And then here's scope number 1. Let's run the simulation here. So this is VN versus Vout1. So here's VN1. Here's VN1. And then Vout1 we can see is out of phase with what's coming in. So I'm putting in about 20 millivolts signal, and I'm on 1 volt per division here in the output. So it is quite a bit larger. So here is the input versus Vout1. And now here is the input. Here is the input voltage, and that looks the same as this versus Vout2. Here we can see that this peaks at the same time. So this output, Vout2, is in phase with VN1. So one input, two equal and opposite outputs. Now, what happens if I put an input of 0? So now I've got both transistors grounded. Current should flow this way down to ground, so the emitter here should be minus 0.7 volts. So let me grab a voltage probe here. So that point is 0 volts. And if I put a probe down over here, we can see that this is minus 0.7 volts. that puts 14.3 volts across this resistor, because the other end of this resistor is 10 volts connected to a supply, and this end is minus 0.7 volts. So this guy has 9.3 volts across him, and he's a 1K, so he should have 9.3 milliamps going through him. Let's check that with our current probe here. So I'm going to put that there, and sure enough, 9.3 milliamps going through the emitter tail resistor. Well, how's it going to split that up? I've got both of these transistors. The bases are grounded, and they're on the same piece of silicone. When they make these, they put these transistors all on the same piece of silicone, so the characteristics are virtually identical. How do you think these transistors are going to split up that 9.3 milliamps? And the answer to that is that they should split them fairly equally. And when I take my current probe over here and I look at the current going down this path, it's 4.62 milliamps, which is virtually half of the 9.3 that was coming down here. And then when I come over here, I can see it's also 4.62 milliamps. So the DC mode, looking at the DC, which we've done basically by putting both inputs to 0, the emitter tail current should be split in two, which each of these guys getting half. 4.6 volts, 4.6 milliamps going through this guy should result in about 4.62 volts across them. So this point sits at 5.4 volts. That's its normal voltage with no input. And this point here also sits at 5.4 volts. So if you have no signal going into these, if I ground both inputs of both transistors, Vout1 and Vout2 should be exactly the same. And by looking at the voltages here and playing with our probes, I can see that that is true. So far, I've been showing you the differential amplifier using only one input, where I've been applying one input to Q1. What I'm going to do now is I'm going to add a second signal generator, and I'm going to apply that input to Q2. So when we applied a signal into Q1, we found that the output off of Q1, off of the collector of Q1, was out of phase, but then we drove Q2 common base, and we got the output off of the other transistor, which was in phase. Put a signal in here. On the same collector, it's out of phase. On the other collector, it's in phase. So that operation should hold true if we put a second signal generator and we put a signal into the second transistor. If I apply an input signal to the base of Q2, I should get an out of phase output off of the collector of Q2, but then for Q1, I should get an in phase output. So let's see if that works. I'm going to pop up my scopes here. But what I'm going to do here for the purpose of triggering is I am going to call this V-scope. I'm going to put V-scope to both channel A's. And what I'm going to do is I am going to connect V-scope to here and V-scope to here. So this enables me to figure out which input I'm triggering from, whether it's VN1 or VN2. And I'm just going to feed that to channel 1 on the scopes. So let's start with applying a signal to VN1. So I'm going to apply this signal in, and it's a 1 kilohertz. It's a sine wave. It's 1 kilohertz, 10 millivolts peak. So I'm going to trigger off of that to the scopes. And then I'm going to look at the output, Vout1, Vout2. So here's Vout1. I'm going to look at that on scope 1, and Vout2 is on scope 2. So run the simulation. That's scope number 1. Here's scope number 2. Put on single trigger there so it gets us a nice stable waveform. So here we are. This is the input that is going to both scopes. because it comes in through here. That's VN1. So on Q1, I have an output that is out of phase with the input. And on Q2, this goes down, this goes down. So the Vout2 is in phase with VN1. Here's VN1, here's Vout2. In phase, out of phase. This is Vout1, that's this point here. It's out of phase with the input. And the other output is in phase with the input. And they're equal and opposite. So now let's take VN1, let's ground that point and bring this signal into Q2. Now this is a triangle wave that is 10 kilohertz, so it's a lot faster, but it's a little lower amplitude. So let's let that go. Now I got to go back to auto trigger here. And I need to trigger on, there we go, I got the input signal. So now I'm feeding this input signal to channel 1 on the scope. So here we are, we have the triangle wave coming in to both of them. That's the signal in. That goes to the base of Q2. And what we can see is off of the collector. So no, sorry, this is the scope down here. So this is the input signal going to the base of Q2 and off of the collector of Q2. I don't know if you can see that. So here's the input signal off of its own collector, Vout2, it is out of phase. But on the other collector, it's in phase. So I'm putting a triangle wave in here and I get equal and opposite triangles on Vout1 and Vout2. Let's get this going. So I put a sine wave into this guy and I get off of Vout1 that's out of phase and Vout2 is in phase. But if I ground that input and then I put a triangle wave into on this side, I get Vout2 is out of phase with the input and Vout1 is in phase with the input. What happens if I put both of them in at the same time? See if I can freeze that to a single trigger. So now I'm putting the sine wave in on VN1 here and then putting the triangle wave in on VN2. And what happens is that the differential amplifier will amplify both signals and add them together and put it on both outputs. So here I can see VN1. So basically this is VN1, this is the sine wave, and here I can see that the sine wave is out of phase with VN1. But so this is out of phase with VN1, but Vout2 here, the sine wave, which is the larger signal, is in phase with VN1. Likewise, you can see that here the triangle wave is at a high point on the triangle. And here you can see that the triangle is a low point. So I got two signals going in and I'm amplifying both of them, adding them together and outputting it onto two outputs at the same time. I just want to point out a couple of details before we move on to the analysis of the differential amplifier. So we measured the current through R5 here in one of the previous slides, and what we found that whatever this current was, the DC mode, when we set both inputs to 0, the two transistors split that current equally. So the choice of R5, the purpose of choosing R5 is basically to set up what's called the emitter tail current, to get a certain amount of current down through this path, and then that will split equally on the two transistors, and then you'll get a voltage drop here, and you can get a normal operating point someplace in the middle of the load line. So if the goal of this is to get a certain amount of current through here, why don't we just replace that with a current source? And that's what we've done on this circuit here. We've taken out R5 and we've just put in a 10 milliamp current source. The other thing you may note on this one here is that although I have one collector resistor here, I've taken this one out and I've basically tied it straight to 10 volts. If you only need one output, so if you want a differential amplifier which has one or two inputs and only one output, then you don't need the second resistor here. Current-wise, it's the same thing. If I put a signal in here and I generate a base current, that'll get amplified and I'll get a collector current down here. I'll get a collector current whether this is a piece of wire or this is a 1K ohm resistor. I'll get the same collector current. The transistor is a current source. It's a current amplifier. If I put a certain current in, I get a certain current down through the collector. So to simplify the silicon level, I don't necessarily need a resistor here. I can just use a piece of wire. So let's see how this works. So far as amplifying a signal, let's try and simulate this one. Okay, so we're running the simulation. Here's my current meter. Make that a little bit bigger, a little bit easier to see. Okay, so let's see down here. I'm measuring the current down the emitter tail here. It is 10 milliamps. And basically I've forced it to that by putting a current source in there. So I'm forcing this to be 10. If both inputs are grounded, then it should split this equally. This should be 5 milliamps, which it is approximately. And this should also be 5 milliamps, which it is approximately. So here I'm splitting the current. The resistors are a little different. So obviously one's a wire and one's a 1K. So it's not going to split it equally, but it's pretty close. So I got 4.82 volt, 4.82 milliamps coming down here. That's through a 1K. So that's going to be about 4.82 volts, which means that the normal operating voltage at this point, just make this a little bigger. So that means if this guy is dropping 5 volts and we started with 10, then this point here should be about 5.18 volts. So this was 4.8 drop, that's about 5.2. So there you go. You don't need the second resistor for it to bias correctly. And we don't need a resistor down here. We can replace it with a current source. So the DC doesn't seem to be affected much by these changes. Let's put in a signal. So there's the signal on. So this one here, this one is V in 1 to V out 1. There is no V out 1 on this schematic. Let's pop this one open. So here's the input voltage. Sine wave coming in, that's on VN1. V out 2 is it's the other transistor, it's the opposite transistor. So it should be in phase, and it is. So V out 2 is in phase with VN1. Now let's ground that one again. And let's put this on as a triangle wave. I'm going to need to change the scope. Let me just change this quick here. So instead of looking at VN1 now, I'm going to look at VN2. So here we are. We can see VN2, VN2 is a triangle wave applied to the input of Q2, which is here, and Vout2, which is taken off its own collector. So it should be out of phase, and it is. So these changes, putting a current source down here and replacing this with a piece of wire, makes no difference to how the differential amplifier works. We still have two inputs and a single output, which is the most common configuration of a diff amp. In fact, when we draw a diff amp, you go into here, when we draw a diff amp in a circuit, we don't normally draw all the transistors and resistors inside of it. We usually break that down into a simpler schematic symbol, which is a triangle where we have a input. We have two inputs, 1, 2. So here's one input, here's one input. So there's my two inputs. Those are these two inputs here. This is the positive input, so that's the non-inverting input. This is the negative input, so that's the inverting input, and this is the single output. So which one is which? So this is the output. So that output represents Vout2 here. This one, if I apply a signal to VN2, I get an inverted output. So VN2 is this point here. It's the inverting input. And then VN1 over here, that's going to cause an in-phase output. So that becomes the non-inverting input. That has a plus sign on it. So we would not draw this whole thing in a schematic. We would draw this where VN1 would go to the positive, VN2 goes to the negative, and then the output is a single output.